Hello there. In this video, we're going to tackle logistic regression, and I've also added a few tabs so that we also tackle regularization and what that looks like when you regularize the model parameters with L2 regularization, and also what it looks like when you separate out your data set into a test and training data set. So we're going to cover all of that stuff in this example. Oh, Yoda. Yes, do or do not, there is no try. Well, you know, in this Excel example, I'm going to do logistic regression. So yeah, I'm absolutely going to be able to do it. And I'll definitely show a few things here in Excel. Okay, so here's what the data set looks like for our problem. These are all normalized to a mean of 0 and a standard deviation of 1. So if you look here across just one of the rows, it looks like we have 10 different inputs. We have one output, but our output is in zeros and ones. So it looks like a classification task. So these sort of output or responses are common when you're trying to answer a question like, is it a cat? Is it spam? In this case, we have 10 different features that are like bullet and armor characteristics. And the question that's being asked, or the classification task, is will the bullet go through the armor or not? So we have a 0 meaning the armor stops the bullet. 1 means the bullet goes through. And we'd like to create a model in order to predict that response. So what we have is we're using a logistic regression model. So you can see up above we have theta naught, and then theta 1 through theta 10. Again, theta 1 through theta 10 are acting upon or multiplied by x1 through x10. And theta naught is our intercept parameter. I've also shown it in terms of neural networks. We'll cover that later, but this intercept parameter, theta naught, can be seen as the bias. That's kind of in the terminology in neural networks. And theta 1 through theta 10 are often called the weights. Okay, so let's go ahead and start to populate, how we make our model prediction. So Z, if you recall, Z is actually going to be, let's see, shift control over, shift control down. So that selects Z. Now we're going to go all the way up to the top. Matrix multiplication of x comma theta. In this case, it's our x's times, theta 1 through theta 10, since we don't have a column of ones. And we are going to add in the intercept after that. So there's our Z values. So again, that's just linear regression. Now with this y hat, we have 1 divided by 1 plus the exponential of, let's do -1 times Z. And another parentheses, enter. Okay, there we go. There's our y hat, our predictions. So now we have y hat, we have y. I'm actually, just to make the loss easiest, let's go ahead and name this y. Okay, looks like it's already named. So y, and then for y hat, if we selected the whole thing, okay, looks like that's already named as well. But if it's not, if it just returns, cells up here, then again, you can name your variables that refer to this dynamic array or refer to a number of cells. So enter. Okay. Now for the loss, we're going to use the binary cross-entropy loss function here. So this is -y times the log y hat minus 1 minus y times the log 1 minus y hat. Okay, enter. Okay, so now we have all of our losses. There is an accuracy column here. So accuracy is just going to be, okay, so y hat is our prediction. But if we want to know exactly, whether the shot will go through or not, we would simply just round that to 0 or 1. So that's what you see here with this round y hat, 0 sig figs. So it's just going to round to 0 or 1, and then it's going to return 1 or 0 if the prediction is correct or not. So you can see in red here, those are the ones that the prediction is correct. Red, the prediction is not correct. And this is 65% accuracy. And to kind of complete everything, we have the average of our loss. Again, I use the hashtag to refer to this dynamic array and select all the values within it. But the average of that is our cost function. There we go. We've completed logistic regression problem. If we started these values at something else, we're going to use the data solver. Again, you'd go up to data, you'd go over to solver, you would select this cost function as your objective function, and you would want that to be minimized by changing all of these theta parameters. So there we go. That's a logistic regression example. Again, it would be called like multiple logistic regression because there's multiple x inputs. Now we're going to go over to, what does regularization look like? For regularization here, we're going to go back and use the let function. That's just going to make everything easier. So first we're going to call out, okay, what are our x values here? And then I'll go back up. What else do we need to know? We need to know theta. So we're going to select theta 1 through theta 10. I'm going to also select one, just call it theta naught. And that's going to be this theta naught parameter. And then we have y, which is over there. Okay. So that's all the values that we need. Alt-Enter puts me on a new line. Now we're going to do, well, z is just a matrix multiplication of x comma theta. So there, that's easy enough. Y hat, 1 divided by 1 plus the exponential of negative z. And then what else do we have? Oh, we have loss. And loss is going to be our negative y times the log of y hat minus 1 minus y times the log of 1 minus y hat. And notice along this whole line, I've already defined all of these variables before in the let function. So it already knows like which cells to go and grab values from to pull into these different functions. And the last part, so Alt-Enter, I usually like to, when you have a lot of formulas in these let functions, just have the last one be what is your output. So you only enter one value, and let's output z here. So enter, there you go. There's all our z values. I can actually copy this and go ahead, paste. In this column, we want to output y hat. So there we go. There's y hat. Paste. And in this one, we want to output the loss. So there we go. That is everything that we just did. Oops, not cost. And now we're going to do the average once again. Okay, so slightly higher cost function here. Again, and and I forget if I mentioned it on the last sheet or not, but I've already optimized these parameters. So these are the optimized parameters. In this case, you'll see that there's only a couple that are very large, either large positive or large negative. If I go back to the other sheet, let's look at this. The same 1 and 3 are large, but so are multiple of the other weights. And so regularization actually dials back all of the parameters, and in doing so, it kind of focuses most on the parameters that play a larger role in the prediction. So let's go back to our regularized model. Okay, so there's the cost function as we defined it in the first example. With the L2 regularization, we have this L2 term. And what this actually is a sum of squares. So we're going to square each one of those values, weight 1 through weight 10, or theta 1 through theta 10, and then sum them up. Okay, so there's the value, and the new cost is going to be equal to the cost from the loss functions, and then you're going to add in lambda times this sum of squares term, this L2 regularization term. And that's actually going to penalize these theta values from becoming very large. And so in doing so, it doesn't allow the model to overfit. It tends, larger parameters, either positive or negative, tend to be associated with a model trying to overfit the data. So here we go. Let's remember this number. L2, this sum of squares term, was 9.17. Just out of curiosity, if we did the sum of squares of all of these, we'd have 48. So much larger parameters in terms of their magnitude, than this example where we added in this penalty term, this L2 regularization term. And then I'm going to go ahead and copy this, and we're going to go to yet another worksheet. So here's the last worksheet. I'm going to go ahead, copy that, copy. Go to this new worksheet, and enter in the loss function. I can go ahead and copy that, paste, enter in y hat. Guess I don't really need to enter z, but just for the sake of completeness, I'll enter z in here. So in this sheet, we actually have a training and a test set. And so one way that you can do this is through randomly selecting a certain number for your training set. So one quick way to do this would be a random array, and then it needs to know in the first entry how many rows should I populate with random numbers. So the number of rows for random numbers is going to be simply the number of rows in our data set. So let's just select the loss column here. Select something with the dynamic array, and then we just accessed everything by putting that hashtag. So random array and the number of rows that are in this data set. Okay, so it actually populated with random numbers from 0 to 1, in as many rows as we have in our data set. And then the way that you might do this is if you want like 80% approximately of your data set to go into the training set, you would do how many of those random numbers are less than 0.8. So now approximately 80% would be, identified as lower than 0.8. And I usually like to multiply by 1 just to have it in terms of zeros and ones. Okay, So that's how you would go about it, and then the test would be 1 minus this. Oops. I forgot you have to put equal before 1 minus training set hashtag to access the dynamic array. And there we go. It's a 0 everywhere that it's a 1 in training set, and a 1 everywhere that it's a 0 in the training set. Now, I've already done this example with approximately, I think, 83% examples. So I've already done this particular example. So I'm just going to choose this, which was off screen, these values for which ones are in the training set and which ones aren't. Now what you want to do is the cost function, you are going to actually, we can use sum product. So what we're going to do is multiply the training. Oops. Once again, forgot the equal sign. We're going to multiply this training array times the loss array. But we also want to divide it by the number of examples in the training set. So that's just going to be the sum of this array. Since, anything that's not in the training set is going to be a 0. So that's going to give us a cost function for the training set. And then we want to do a cost function for the test set. So what we want to do here is hit F4, and that will, again, include those dollar signs so that array won't change. And now we can go back here and just drag that over. So there's actually the cost function for the test set. Now, what you would do in this sort of setup is, again, we're going to do the sum of squares of these values. 30. So it's a little less than that first example, which was, upwards of 45 or so. So it's regularized it a little bit by dialing down these parameters. You can see that still 1 and 3 are probably the most important in making the prediction. And then the new cost is going to be simply this cost function from our training set, the losses in our training set. And then we're going to add lambda times the sum of squares of these parameters, which is kind of a penalty function. And the interesting thing here is when I talked about hyperparameters, you can't just select hyperparameters, so you like to have a holdout set to allow you to select the best hyperparameters for your data set. So in this example, I actually, off to the side, I put a number of different lambda values, and then I optimized, using this cost function up here, I optimized the parameters, and then I actually recorded the cost function of the test set. And so this test set can be used to select which value of lambda should I choose to regularize this logistic regression model. So here, if you see, the lowest is this 0.0002, which is the lambda that I've used in this example. So with that, that's just a few examples of logistic regression of regularization using an L2 regularization on the theta parameters. And then, in this last example, just separating it into two sets, a training and a test set. So with that, hopefully you learned a little bit about logistic regression. And, next we can really move into neural networks, because logistic regression has both the linear regression part as well as this sigmoid activation function. And so that really describes the two different parts that you have in nodes of a neural network, which are the linear part and then the nonlinear activation function. So with that, may the course be with you.